This one is a little bit more technical, but it is along the same lines of cycle consistency. The method is unit on supervised image-to-image translation. What we just covered with cycle consistency was also for unsupervised image-to-image translation networks. But what are both of these trying to do? There is some joint distribution on the entire space that is generating images from domain 1 and domain 2 in a joint fashion. But the information that you have is you don't have any information on the joint distribution other than the marginal ones. You have only samples from each one of those two domains. And the idea is that you want to learn that joint distribution. But there is an infinite set of possibilities. So infinitely many, or perhaps uncountably many distributions on the joint distributions between domain X and Y are going to have identical marginals. Think of the shadow of a person on the ground. From the shadow, it's very hard to say what was that person. It's just a projection from a 3D object to a 2D object. It's the same story here. With joint distributions, you have a distribution on X and Y, but then your data is on X only and Y only, the marginal distribution of X only and marginal distribution of Y only. So there is infinitely many possibilities. There is this shared latent space assumption that's going to help you a lot. You're not going to be able to find all of such distributions, but perhaps you can find distributions that operate given a shared latent space. What do we mean? There is a Z here that is going to generate both X1 and X2 from two separate domains. Maybe one image is taken in a winter, the other one is taken in summer. So the same Z is going to generate two images. This is called the shared latent space. And the entire framework that we're going to have in front of us is actually trying to train G1 and G2. To train that, you're going to have some encoders. This is encoder 1, encoder 2, and then you're going to need some discriminator. You're going to assume that Z is given by X1 and X2 when they are being pushed through your encoders. This is going to be really hard to enforce exactly, but that's actually the role of the loss function that we're going to be writing soon to make this happen. Then if you take Z, push it through G1 and G2, that's going to give you two images, X1 and X2. And it turns out that this shared latent space is going to imply cycle consistency. So the cycle consistency condition is a subclass of shared latent space constraints. Why is that? What is the proof? Let's say you have an image X1. You're going to use E1 to take you to Z. You're going to use G2 to give you X2. You're going to take X2, use E2 to go back, and then you're going to use G1. And it's going to bring you back to the location that you wanted. So E1, G2, let's call it this function. It's going to give you a function. And then E2, G1 is going to give you another function, E2, G1. And these are inverses of each other. So shared latent space constraint implies cycle consistency. The reverse is not true. Okay, I guess it's a good time for me to stop. For those of you who have questions, I'll be around.